Hey there, ever looked at a chemical formula and thought, what on earth is that? It kind of looks like an alien language, right? Well, today, we're going to change all that. We are going to decode the language of chemistry and turn that gibberish into, well, into something you can read like a total genius.
All right, take a look at this thing on the screen. Seriously, 5, then NH4 in parentheses with a little 2, then an O. I mean, it just looks like a total jumble of letters and numbers, right? And if you think it's intimidating, you are not alone. It's totally normal. But here's the secret. There's a really simple logic hiding in plain sight.
So that's our mission for this explainer. I'm going to give you the keys to crack this code. We're going to break it all down piece by tiny piece. And by the end, you'll be able to look at any formula and know exactly what's going on. Sound good? Okay, let's do this. Okay, first things first. Our decoding mission starts with a big question. How do you spot an acid? What makes something an acid in the first place? Well, the biggest clue, and I mean the biggest one, is almost always hiding right at the very beginning of the formula. We're on the hunt for one specific element.
And surprise, surprise, that element is hydrogen. So the classic textbook definition of an acid is any compound that spits out hydrogen ions, that's H+, when you dissolve it in water. But here's what you really need to remember. If a chemical formula starts with an H, your acid alert should be blaring. It's your first big sign.
Now, acids aren't all the same. They kind of come in two main flavors. First up, you've got your binary acids. Super simple, just hydrogen plus one other nonmetal element. Easy. Then you've got the ternary acids, which people often call oxyacids. These are a little more complex. It's hydrogen bonded to a whole group of atoms called a polyatomic ion. And yeah, that name oxyacid is a dead giveaway. It's always got oxygen in it.
And this is a perfect way to see the difference. Look on the left, HCl. Just two pieces, right? Hydrogen and chlorine. That's your classic binary acid. Now look on the right, H3PO4. Whoa, that's a much bigger structure. You've got hydrogen, phosphorus, and oxygen. That's our ternary acid. And you guessed it, each type has its own special naming rule.
So, two types of acids means two sets of rules to learn. But don't worry, we'll start with the easy one. Let's crack the code for those simple binary acids. It's a really straightforward three-step process. You'll get this in no time.
Okay, here's the recipe. Step 1, you always start with the prefix hydro. Always. Step 2, you grab the root of that other element's name, like chlor from chlorine. And then step 3, you just stick ic acid on the end. So it's hydro, root, ic acid. See? Simple as that.
All right, now check this out. This is where you see that rule in action. And it's pretty cool. HCl becomes hydrochloric acid. HI becomes hydroiodic acid. You totally see the pattern, right? The name is literally telling you what's in the bottle. Hydrogen and one other thing.
Okay, ready for level 2? Let's talk about those oxyacids. Now, they might look more complicated, but I promise, their naming system is just as logical. It all comes down to one little detail, the ending of the polyatomic ion's name.
And hey, to help you remember this, we've got this awesome kind of silly little saying. If you ate something icky, you might get ussy. I know, it's goofy, but it works. Just remember, ate becomes ick, and ite becomes us. Let's see how that plays out.
So here's how that silly phrase turns into an actual rule. If the ion's name ends in ate, think sulfate, the acid name ends in ic acid. But if the ion name ends in ite, like sulfite, the acid name ends in us acid. Makes sense, right? Let's look at some real examples to lock it in.
And boom, this table lays it all out perfectly. Look at H2SO4. It comes from the sulfate ion, so we call it sulfuric acid. But right below it, H2SO3, that comes from the sulfite ion, so it becomes sulfurous acid. It's like a two-way street. The formula tells you the name, and the name tells you what's in the formula. All right, nice work. We've pretty much mastered naming acids. But to truly read any chemical formula, not just acids, there's one more skill we need. It's the final challenge, counting every single atom. This is where we learn to read the chemical recipe for real.
So our first tool for counting is something called the subscript. You know that little number that hangs out right after an element symbol? Its job is super simple. It just tells you how many atoms of that one element are in the molecule. That's it.
Let's use an example everyone knows. Good old water, H2O. See that little 2 after the H? That just means there are 2 hydrogen atoms. Simple. And the O? Well, it doesn't have a number. And in the world of chemistry, if you don't see a number, you just assume it's 1. So H2O, that's 2 hydrogens and 1 oxygen. Easy peasy.
Okay, but what about those pesky brackets? You know, parentheses. What do they do? Well, think of them like a multiplier in math. They multiply everything that's inside of them. Let's use a bigger example to see how it works. Barium phosphate.
Let's break this monster down. The Ba3 part is easy, right? That's just 3 barium atoms. No problem. Now for the brackets. Inside the parentheses, we've got 1 phosphorus and 4 oxygen atoms. But look at that little 2 on the outside. That means we have 2 of that entire PO4 group, so we just multiply everything inside by 2. 1 phosphorus times 2 is 2 phosphorus atoms, and 4 oxygen times 2 is 8 oxygen atoms. See? Not so scary. Okay, one last number to learn, I promise. It's called the coefficient. This is the big number that you see out in front of the whole formula. So if the little subscript tells you what's in one molecule, the big coefficient tells you how many of those entire molecules you're working with. It's like saying you want to make a double or triple batch of a recipe. So think about it. If H2O is 1 molecule of water, what do you think 2H2O is? Yep, it's just 2 separate molecules of water, just like you're seeing here. That big 2 out front multiplies the whole recipe.
Let's actually do the math together on this one. If we have 4 H2O, how many atoms of each do we have? Well, to find the total, you just multiply the big number, the coefficient, by the little number, the subscript, for each element. So for hydrogen, it's 4 times 2, that's 8 hydrogen atoms. And for oxygen, it's 4 times its invisible 1, which is 4 oxygen atoms. All in all, that's how you get the grand total.
And that's it. Just like that, you have all the keys to the kingdom. Remember that gibberish we looked at in the beginning? It's not gibberish anymore, is it? You now have the skills to look at it, read it, understand it, and count every single atom. Mission accomplished.
So let's do a super quick recap of the codes we just unlocked. For those simple binary acids, it's the hydroic acid rule. For the more complex oxyacids, just remember our silly phrase, ate becomes ic and ite becomes us. And for counting atoms in any formula, you just multiply. The big coefficient times all the little subscripts. And don't forget that brackets multiply whatever's inside them.
You know, you came into this looking at a formula that probably seemed impossible. And now, you have the tools to translate it. You can literally look at the world differently. The ingredients in your food, the compounds in your medicine, all the reactions happening around you, it's a whole new language. So the only question left to ask is, now that you can speak chemistry, what new conversations are you going to understand?